All right.
Too minimalist.
Those of you who are on marine biofilter, guess what? We are beaming logic class into your living room. And as I was just saying a second ago, we have the next whole couple of weeks all planned out actually in this class. Do you want to hear what the plan is, or do you want to just be surprised every day?
I want to hear the plan.
The plan. Today, you're doing a bunch of random little thingies, which I've listed up there. Kind of a catch-up day. We're going to do some hard proofs. We're going to go over the quiz. We're going to do something. We're going to do we're going to do lots of practice, which really sucks if you're not here. Oh well. And this is going to be our last big, get good at predicate logic in class day. After today is if you're not good, you still have to, you have to do it on your own. Then building up to Wednesday, which is going to be one more day with me talking, in which we're going to do this really hard thing, which is really cool and interesting and really important. So I'll leave that as some suspense. Friday, we are going to hear a presentation from Jason on piano arithmetic, which is an interesting topic. Some of you might know something about. And also, we're going to cram into Friday another presentation by Noah, who just found out about this 10 minutes ago. He is going to do a presentation on the biographies of some of the people that we've been hearing about. In particular, Cauchy, Weierstrass, Bolzano, Dedekind, and Piano. So we're going to get extremely detailed information about all 5 of those guys, where they came from, what their deal is, what country they were in. And we're going to become basically experts on late 19th century mathematics. And we're going to basically learn that everything converges kind of in Germany, and that's where everything's happening. So that's happening Friday. Next week, we are going to... I was kind of lying when I said I planned out several weeks in advance. Next week, I planned out this week. Next week, then we're going to have presentations by you guys next. You sent me an email, right? Yeah, I didn't respond yet, sorry. But so we should meet soon. We're going to have a presentation on, you guys are doing the one on Cantor, right? Yeah, you and Yanni. Yep, you and Yanni. So that's really important. We're going to learn about things like accountability and uncountability, which some of you might know something about, but some not. And then we're going to take that, we're going to run with that pretty far. And then one other day next week, I guess it will be Thursday, or vice versa, I will be I will again take a one whole day to talk about the semantics for predicate logic. Which is something, if you recall, in the day that we introduced predicate logic, I just said, this is kind of what it means, loosely speaking, and then we just kind of went with it, right? But what I didn't ever explain is how you can actually determine whether something is true. So the truth table analog for predicate logic is actually kind of complicated, and it's with models, and it's important. If you took a more advanced logic class in college, in a math department, this is what you'd spend you'd spend weeks and weeks and weeks on this. But we're going to just kind of do it a little informally, but it still takes one whole day. And that's going to prep us for some of the stuff that happens in the 20th century. So that's what's going on the next 2 weeks. And then at that point, it just becomes presentation, one per day, every day, straight to the end. And we're going to read a lot of chapters, and there's a comic book coming up also. Okay, so what I wanted to actually, so now we're going to really start learning. What I wanted to do, and I think this is awesome, an amazing opportunity, and one way to really understand the flavor of late 19th century mathematics, and actually current mathematics, we're going to prove the intermediate value theorem. Oh yes, we are. Not with this marker, we're not. Right. What's up? Oh yeah, things got chaotic at the end of the lecture on Thursday. I blame myself. They were immaculately prepared. I stole all their time with rambling as usual, and then they tried to cram it into the end. We're gonna go back to that a little bit, maybe for 5 minutes or so, or 10 or something. But now I wanted to do this. By the way, they also prepared a proof of the intermediate value theorem, and I have no particular reason to think that my proof is any better than what Brian Morrison, Raymond, and Noah did. Nonetheless, I know my proof is good, and theirs probably is, so we're going to do mine. Yeah. So the intermediate value theorem, let's go all the way back. What is the intermediate value theorem? If you have a continuous function, yeah, we're just first we'll just kind of draw a picture.
Then and you have 2 points that are on different sides of
2 points that are on different sides of another point or something. Okay, someone else take over. Good start.
A and a B.
Yeah.
F of A and F of B.
Yeah.
Then for any K between F of A and F of B, there must be like a C between A and B, so that F of C is K.
Yeah. Exactly. That's what it meant. Good. Yeah. If you have a continuous function and you have 2 points A and B, and you know, you have f of a and f of b, and they're not the same. Doesn't matter which one happens to be higher or lower. If you give me any y value in between f of a and f of b, then if this is a continuous function, somewhere the curve must cross this line, which is another way of saying there exists a point C such that f of c is k. Okay, so I'll just write all this out just real quick. If f is continuous on a closed interval AB, then for any intermediate value between f of a and f of b, so if there is some k between f of a and f of b, then there exists, I guess for any k, then for any k whatsoever, it is true that if k is a number between f of a and f of b, there exists a point C on the interval AB such that f of c is k. Okay, so several things to say about this. One, you all have seen this before, so that's good. In calculus, we use this theorem a lot in calculus. We did not prove it in calculus, and in fact, basically no one proves it in first year calculus. You don't even think about proving it in a class, in like a normal AP Calc class. But even in like super whatever craziest college you can think of, MIT, blah, 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 first year calculus, they do not prove this theorem. It is one of those theorems that just doesn't get proved the first time around. The second time around, when you take an analysis class, then this is exactly the kind of thing you prove, and this is why we're going to do this today. And the main reason why we don't prove this, I kind of told you this last class, or they did. Why don't we prove this in analysis 1A, Ramya?
We didn't have the axiom of the
Yeah, we didn't prove this because we're totally unprepared to prove this. Because in order to do this proof, you need to know a lot of information about the real numbers, and in particular, the completeness axiom, what I'm going to call the least upper bound axiom, says, which is a certain property that the real numbers have, which was a property that was not recognized until the 19th century. After it was recognized, it was essentially an axiom, just like Euclid. What does he do when he's trying to prove something and he can't figure out how? He eventually boils it down to something that he's going to need to do his proof, so he says, okay, let's make it an axiom. So just like Euclid, again, this is how mathematics works, at least the axiomatic method in mathematics works. Cauchy and Weierstrass, they kept trying to do these proofs because they wanted to, and they kept finding that they needed some extra piece of information in order to be able to execute the proofs, and that missing piece of information turned out to be the least upper bound axiom. And so they just postulate it as one of the very properties of the real numbers so that they can execute all these proofs. And suddenly all these proofs are now doable. Intermediate value theorem, the extreme value theorem, the Bolzano-Weierstrass theorem, the what's it called? Boundedness theorem. If there's an upper bound, then or if it's bounded above and increasing. If it's monotone and increasing, then it has a limit. Yeah, then it converges. Yeah. Okay, so I thought we would do this one, and I think you guys can handle this. Actually, it's hard, but it's within your ability. It still takes like 15-20 minutes. So all right, what is So let's go. Oh, also, do you want the big picture idea first and then do the proof?
Yeah.
Okay, so I think that actually works kind of better. So we're going to draw pictures, and then the pictures are going to inspire the proof, and I'm going to be moving all around the room. That's a perfectly terrible way to have to do this if you're watching at home. Hope you're learning some marine bio. All right. The basic idea. This is the idea. And by the way, for some of you, the idea you might be perfectly happy with the idea. You don't see the point of doing the proof at all. So that's fine too. But once you get the idea, the big idea, then the proof is actually not that hard. It's just some technical details. Okay. So here's the idea. I have some function. I have so this is f of a, this is f of b, and I'm going to introduce some number u, and u is some y value in between f of a and f of b. Okay, so here's what the function looks like, and it's continuous, so it's all connected and stuff. And now, what we would like to argue is that somewhere this function crosses this line, that there exists some point c where f of c is that number. Okay, well, here's how we're going to do this. We're going to take all of the x values, we're going to construct a set, and that set is all the x values which, when plugged into the function, land below this line. Okay, so here's this line, and this is some point or whatever, and what we're going to do is we're going to take all of the numbers which, when plugged into this function, are less than u, and we're going to call that s. So what is s? S is, let s be the set of all x such that f of x is less than u. All right. And then I sort of think of the real numbers as having this kind of property that if you take all the numbers which are less than u, like the next point or something like that, has to actually have y value u, right? And I am unable, without the least upper bound axiom, to say that, but with the least upper bound axiom, that's exactly what I can do. I can take the least upper bound of this set. And what is the least? Okay, so I'll just do that now. Let C be the least upper bound of this set S. In other words, of all of the numbers which, when plugged into this function, return a y value which is less than this magical number u, take the least upper bound of that set. What does that mean again? And now C is of course an x value, right? Because this is a set of x values. So C is the x value which is bigger than all of the numbers in this set. So it must be somehow like over there somewhere. And of all the numbers which are bigger, it's the smallest one. Does that make sense? Okay. So basically the whole gist of this proof is to prove, if I can prove that f of c is u, then I would be done. This is my goal. Because what the least upper bound axiom enables me to do is to make this step right here, right? I'm allowed to say that the least upper bound of a set of real numbers is also a real number. In other words, such a number exists. This is the only moment at which I use the least upper bound axiom. That there exists a number which is the least upper bound of that set. And if so, then I can prove that f of c is u. How can I prove that f of c is u? By the way, if I prove that f of c is u, then I have proved that the function does cross that line. Well, yeah.
So we can suppose that f of c is not u.
Yeah. You said, sorry,
That
two
is-
people talking at once.
We can suppose that it's great. We know it's not less than u, so we can suppose it's greater than u.
Yeah, basically you do it by contradiction, right? How do we know that f of c is u? Both the assumption that f of c is less than u and the assumption that f of c is greater than u lead to a contradiction. For sort of subtly different reasons. So we have these pictures, and Schwartz kind of recommended this approach a little bit last year. He and I talked this out. So suppose, just give him some credit, suppose f of c is less than u. Okay, what does that picture look like? That picture looks something like this. Here's A, here's B, here's f of A, here's f of B. And now I have some number u, and I have the function what it must do somehow is I have this set S, right? And so if you think about what this set S is doing, everything in this set S, and then there's this point C, which is the least upper bound. Everything in this set S must land below line U, because that's how S was defined, as the set of all x values which when plugged into the function are less than U. Okay, but if f of C is less than U, then not only do all the values in this set land below the line, but so does the point f of C itself lie below this line. But then what must this function look like? Because if S is precisely all the points which land below U, then all the points that are not in S must land above U. Or on U. Right. I guess it could go on maybe or something like that. But so this is the picture determined by the assumption that f of C is less than U and S is the set of all numbers which when plugged in the function lie below U. What's wrong with this picture? It's not continuous. Okay, so again, this is the intuitive proof. So the intuitive proof is if I draw the picture such that everything in some set S lands below U, and then f of C is also less than U, and thus all the points not in S when they're plugged in land above U, I get something which looks discontinuous. So now let's patch it. This was Schwartz's idea. Make it continuous. But the only way to make it continuous is to kind of like drag that top piece down a little bit, right? So I'm going to patch the continuity. But in patching the continuity, this is C. Now I have something that looks like that. What is wrong with this?
Those points are below you. All supposed to be the same.
Yeah, there are points. What's the contradiction lies, can I get a yellow pen and red marker? The contradiction lies right over here, right? This is the problem. This becomes a problem. Right here becomes a problem. What is exactly what Amy was saying it? Amy, say it louder.
That there is a value that's greater than C, so that value is still less than U.
Yeah, exactly. And since we're doing it informally, we're going to say there are points which are bigger than C, such that or there are points bigger than C. How did I write this? Yeah, there are points bigger than C. That are in S. I guess is the simplest way to say it. There are points greater than C that are in my set S. Why are points greater than C in set S? Because according to our picture, there are points greater than C which have a y value less than U. Thus, they must be in the set S. But what's wrong with that? C is the least upper bound, and let's be precise. What particular property of C being the least upper bound am I using? That's kind of an awkward way of phrasing it. Where is exactly, point exactly to the contradiction?
C is greater than any element of that.
Right, actually we're not using the fact that it's the least upper bound, we're using the fact that it is an upper bound, right? But C is an upper bound. Remember, saying you're the least upper bound is really saying two things. It says one, that you're an upper bound, and two, that you're the least upper bound. But C was defined to be the least upper bound, but right now I'm just using the upper bound part of it, right? If C is an upper bound, then that means C is supposed to be a number which is larger than every number in S. But here I have numbers which are bigger than C that are still in S. This is a contradiction with the upper boundness of the point C. Follow? No.
Couldn't you do that quicker? Because just by supposing that f of C is less than U, you're putting C in S, just like with your first statement.
Right. I actually haven't said that C is not in S.
But you said C is an upper bound, and does it an upper bound?
Well, yeah, an upper bound. So an upper bound can be in the set, right?
Yeah.
The least upper bound of all the numbers, like 1 to 5 inclusive, is 5. So yeah, so yeah, cool. Okay.
How would you do that stuff formally, like patching?
Oh, we're gonna do that in a second.
Oh, you're actually.
Yeah, I'm gonna actually do it because it's not that hard. You're just some epsilons and deltas and crap. But I want to do. I am differentiating for multiple audiences. So this is the actual idea, and then we'll also do the technical proof, which is not that hard. It's technical. Okay. So on the other hand, suppose f of c is bigger than u. Okay. Well, now if f of c is bigger than u, that's also going to lead to a contradiction. Why? Well, here's A, here's B, here's f of A, here's f of B, and so we have some point u. Well, if f of c is bigger than u, then again, so here's u. Well, now it's like, well, I guess by the time I get to c, I'm bigger than u. But all the points to the left of c have to be less than u. And so now my picture kind of looks like that, right? Because again, that's how we defined it. We defined all these elements, all the x values in this set S to be when plugged into the function less than u. F of c is the least upper bound, f of c is bigger than u. But again, what's the problem? It's not continuous, right? So to patch the continuity, we're forced to do a patch, and the patch is going to look like this. So here's f of A, here's f of B, A, B. You're getting all this, right?
Yep.
Here's U. Well, now the patch, if f of c is truly greater than u, the only way to make that happen is to pull this piece up, right? But if we pull that piece up, so this was this, and this was c, now where's the problem, and what is the problem? Now it's not a least upper bound. Exactly. Now this little area becomes the problem. The numbers which are bigger than c and above the line, or less than c rather, but are above the line, because now we have points which are less than c, which are upper bounds for s, which are upper bounds for s. In other words, if you are bigger than, or rather, so if you are, what did I try to say? Points less than c. Oh yeah, points less than c. Yeah, because c is, my picture is actually a little bit weird. There we go. So there's c. Now I have points which are less than c, because that's f of c after all, less than c, which are larger than u. Well, that's a problem, right? Because if f of c or f of points a little bit less than c are larger than u, well then those points are in fact upper bounds for s, because s is a set of all points which land less than u. But then c is an upper bound here because because c is bigger than all the points that are in s. But now I have points which are which are upper bounds for s, or I guess, well, now it's kind of hard to do this because we're in the absurd world, so anything I draw is going to be wrong. But I think, Didier said it right. Now we have points which are less than c, which are upper bounds for s, and this is, but c is the least upper bound. And now it's specifically what we're contradicting is the leastness of it, right? I now have another number, which is, okay, so that's contradiction. All right, that was the big picture. If you get that, I mean, that means you're basically doing analysis right now. And so good job. If you crave the details, which I'll pretend that at least one person does, then we can do this. Yeah, so 2 people crave the details. So the details look like this. Well, and here comes the full 19th century rigor on display. Again, here comes the proof. This is what I want to prove. Okay, so we start, right? So suppose f is continuous on the closed interval AB. without loss of generality, let f of a be less than f of b. That's just a way of saying, you know, let me do that, and if you don't like it, do it the other way. It's like a proof by cases, but you don't do the second case because it's the exact same proof. Now also let u be some y value in between f of a and f of b. Okay. Well, good. That's my assumption. But now, if it is a continuous function, I am now going to lean on the formal Weierstraussian, Cauchyan definition of continuity, which is what we learned in analysis 1a. So since, and I'm going to do it specifically, I guess, at point C, because point C is the key, is where everything happens. Every time I wake up, since you ate too much giant pot of lunch that you eat at 9 a.m. every day, since f is continuous at C, what do we know? Well, we know that for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, this is just the definition of continuity. I'm basically just saying that the limit at C is f of C. If the difference between x and C is less than delta, then the difference between f of x and f of C is less than epsilon. Okay. So this is, note how I'm taking this beautifully intuitive and geometric thing called continuity, and I'm reducing it down to a tedious, complicated statement of arithmetic. This is essentially the arithmetization of analysis. I don't need pictures. I don't need to understand what continuity means. I don't need to draw anything without lifting my pencil off the paper. Continuity just means, say, the 19th century mathematicians, this terrible, terrible statement of the existence of numbers in certain intervals and certain logical arrangements. All right. So if you accept that, then I can do this proof. Okay. How do I do it? By cases. Oh wait, one more thing. So good. Now I'm going to do the same thing I did over there. I'm going to say let S be the set of all x such that f of x is less than u. And I'm again going to say let C be the least upper bound of that set. And this time I want to be even more explicit about what exactly that means. So help me out. What does it mean to be the least upper bound of a set? It's really like sort of two things. It's an upper bound. And it's the least upper bound. Okay. So how can we write that out in quantifier language that C is an upper bound? So C is an upper bound means what?
There's just, I don't know quantify, it's like there's a set of upper bounds and out of all those the values in that set is the least.
Right, but so you're doing something called just being smart and trying to do math like a normal person, but what I'm trying to do is rigor. So I want every damn thing written on the board because this should be something that like a computer should be able to do it, right? It's just manipulations of symbols. I mean, this is what the 19th century math is all about. So what I want to get it on paper. What exactly do I mean when I say C is an upper bound? What's the definition of upper bound? Yeah, Ben Felder.
For all elements in S, C is greater than S. Yeah.
Yes, for all x. If x is in S, then
C is greater than S.
yeah,
Greater than
or equal to. Yep, that is exactly what it means to be an upper bound. You're an upper bound if you're simply larger than or equal to all the elements in that set. Okay, and now what does it mean that C is a least upper bound? And I'll make this heavy, because now I want to talk about the leastness of it.
Can you use upper bound, or do you want to just define from just a second?
We can just go straight from the beginning.
So it's like for all k, such that if x, for all k, for all x, if x is an element of S, then x is less than or equal to C.
Wait,
C is
what
less
happened to
than
K? Wait, what's K?
K is all the other upper bounds, and you're just saying that
Right, so for all K,
such that And for all x. Or,
Yeah.
yeah.
Okay, yeah, actually, on my paper, I realize now that I did this all in one big step. So that's why this is not making any sense. So yeah, so I already have the x. So for all x, so what does it mean if c is an upper bound? It means that for any number whatsoever, does this make sense? Yeah. For any number whatsoever, it's an if x is in, then c is bigger than it. If for any number in the set, c is bigger than it. And I can say for all, she wants to use k, we can use y, it doesn't matter. If you're an upper bound, then you're,
Then c is less than.
then c is less than u. So for all y, if, when, no. What the hell am I doing?
Yeah.
Put this paper away.
Yeah,
Excuse
just
myself.
right.
For all y, if x is in S, basically I want to say if y is an upper bound. Am I doing this right? You captured on video, I hope so. Then
It's greater than or equal to c.
C is less than or equal to y. Yeah. Okay. Boom, boom, boom. Okay, yeah. Whoa, quantifier logic. Yeah, so what does it mean to be the least upper bound? It means for all x, c is an upper bound, and for all x is bigger than c. And for any number y, if everything in S is less than y, in other words, if y is an upper bound, then c has to be less than or equal to y, because c is the smallest one. Follow? Okay. All right. Sorry that took me so long. Good. So I now have my assumption that it's continuous. My assumption that there exists some number in some interval, just a bunch of arithmetic. I have my definition of continuity. I have my definition of set S. I have my definition of set C. And this is the particular moment at which I use the least upper bound axiom. And this is the definition of what a least upper bound is. Okay, now it's just a matter of just putting all this arithmetic and quantifiers together in some kind of arrangement and getting what I want. And what is it that I want? It's the same thing I wanted on the back board. I want to show that indeed that magical number that the intermediate value theorem claims exists is in fact the least upper bound. So I want to show that f of c is u. And thus I have proven the existence of this particular point where it crosses the line. That point is the least upper bound of the set of numbers which land less than it. Okay, so we have two cases just like before. Case one is we assume that f of c is less than u. Okay. All right. Well, should I do a picture? I feel like a picture would be a good idea. It's that same picture though. If f of c is less than u, then what I want to do, okay, so remember over there when I said you have to patch it? So if we go back over here, flip the camera back. If you go back to this picture, because I don't feel like drawing it again, then the problem is in this picture. This is the picture which matches all the information we have at the moment, right? F of c is less than u. All the elements in this set S are less than c, and everything in S lands below the line.